Welcome everybody to this presentation on neural synthesis of binaural speech from mono audio. My name is Alex, I'm a research scientist at Facebook Reality Labs in Pittsburgh, where we care about social telepresence, social presence in virtual reality. If you are in virtual reality, your experience does not only depend on what you see, it heavily depends on what you hear. So it is important that we can render audio in a physically highly accurate way. That means audio is spatialized. I need to get the position from which the sound is coming, right? There are some individual aspects, your specific head shape, ear shape. They do transformations to the sound which impacts how you perceive sound. And we need to model all of this in a correct way. If you look at traditional systems, they all come with some drawbacks. It's essentially a stack of approximations with linear time invariant systems. Like what your ears do, for example. It's measured in an anechoic chamber, so you need something like that. And then it's only measured at fixed spatial positions, and you need to interpolate between these positions. You have crude approximations to room models, shoebox models, for instance. You do not really model speech directivity well. These systems work great because they are applicable to any kind of audio. However, in our scenario, we have in-domain audio. We are interested in speech, in conversational audio, right? And this is because it is in-domain, it gives us the opportunity to actually capture data and then learn from data in an end-to-end fashion. And this is what we do here. You see me on the bottom. I'm talking to a mannequin that has binaural microphones in their ear, and I myself have a microphone so that my transmitter signal can be captured. And I'm walking around, so we get continuous time data with like moving trajectories through space. We do this with 8 participants, 2 hours. We release the data set, have a look by the way. So we get end-to-end data for the sound spatialization task, constrained on the domain of speech. And this is what we are working on. And this is what this presentation will be about. How can we get this spatialized sound data, and how can we learn from this data and have a highly physically accurate system that is more accurate than traditional signal processing based systems. Okay, let's start talking about the network in general. How does it look like? We have as input the transmitter signal, which is a mono signal, and we have the transmitter and receiver head position and head orientation, so that we can, know their relative position to each other and spatialize. The output is a binaural signal, left ear, right ear audio signal. What would the receiver hear with their own ears? And our network has 2 major components: a neural time warping component that takes care of, the time that sound travels, interaural time differences, stuff like that, and then a temporal convolutional network that adjusts frequencies and does some minor phase adjustments. Let's talk about neural time warping first. The input here, transmitter signal, you see it in white, and the idea is that sound takes some time to travel through space. So let's compute this time and then take samples from the transmitter signal, for example, time 50 on the transmitter side. And then based on the distance between transmitter and receiver, we might know that this sample would happen at time 100 on the receiver side. So we map it, we warp it to that place. Obviously, transmitter and receiver change their position in space dynamically over time. It's not always the same position, so they could move closer, which means we do not have to warp over a span of 50 audio samples or whatever it is, but less than that. This is the basic idea of warping. However, there are physical constraints with sound that we do not want to break with. One is clearly causality, right? So if I say something, you will hear it after I said it. Meaning, whatever we warp, whenever we want to figure out which sample do we have to take for position T on the receiver side, we have to look at some position that happens before T on the transmitter side. In other words, we do not allow time travel. We do not allow to warp from some future audio to the current time. The second constraint is monotonicity, meaning we want the samples to stay in the same order that they were on the receiver side. So it's fine if we take sample 30 and map it to time 50 and then take sample 40 and map it to time 51, because maybe both of them moved closer together, so the span has to be decreased. But we do not want to allow to flip signals. This is technically possible in a physical way if you would accelerate and would get faster than the speed of sound. But in practice, this does not happen, right? When we talk about person-to-person communication. So these are the 2 constraints, causality and monotonicity, that we want to maintain with our warping module. Our warping module has two components. One is geometric warping, the other one is neural warping. The idea of geometric warping is fairly simple. You have the transmitter, you have the receiver. In order to compute for each ear of the receiver how many samples we have to warp the signal by, we just take the current time frame, we compute the distance between transmitter and receiver, multiply this with the audio sampling rate, divide by speed of sound. That is the number of samples that pass in order to get from the transmitter to the receiver over that distance. And that is the number of samples then that we have to warp. This is clearly causal, right? Because we have t minus some positive value, will always be smaller than t. It's also always monotonous unless you accelerate faster than speed of sound, which we do not do. But this has very strong limitations, right? If I just turn my head, there is no direct way to my left ear anymore. So geometric warping would fail now because sound has to travel around the head, and this is nonlinear dependencies that geometric warping cannot model. Even worse, if the transmitter turns the head, there is no direct path to either the left or the right ear anymore. And sound also has to travel around the transmitter's head. That's why we use neural time warping. Apparently it depends on the head orientation and head position of both transmitter and receiver. So this is both the input to the network, then we have, like in our case, a 4-layer temporal convolutional network, and the output is a warping field, like for each time frame t, from which sample in the source signal do we have to warp. We basically, as our final warp field, we use the output of geometric warping plus neural time warping, meaning geometric warping will give us a coarse estimate, and then neural time warping will give us a more fine-grained estimate. The problem is we have to stick to our constraints. We have to enforce our physical constraints. We do this by having a recursive activation function. How do we get causality? Well, we have the minimum of the current frame and whatever our warp field predicts. This way we make sure that the network output, which could potentially be unconstrained, is always causal. And monotonicity? Well, monotonicity says that our current warping value has to be at least as big as the previous one, so we do not change the order. And this is maintained by taking the maximum of the previous value and what we predict right now. So it is a recursive function, a recursive activation function that makes sure that all these constraints are maintained. Let's have a look at an example. You see the receiver and transmitter here on the right side, and the receiver has turned the head, so there is no direct path to the left ear, meaning geometric warping will make errors and we will have to correct. The sound needs more time to travel to the left ear than geometric warping would predict. Let's have a look at some actual waveforms. In white you see the transmitter, and then in blue you see the left ear and right ear of the receiver. And if we now do only geometric warping, you see that the peaks from the mono transmitter signal are kind of well aligned to what you would expect on the binaural recordings, but there are some misalignments. If we do the neural warping on top, you see, let me switch forth and back between the two, you see that we get a better alignment to the peaks in the binaural ground truth recording. And you also see, if you look at the left ear of the receiver, that neural time warping says, hey, we have to shift everything a bit more to the right, meaning there is more time passing until the signal arrives at the left ear, because it has to go around the head. So much for neural time warping. The second block is a temporal convolutional network. It's essentially a wavenet, so I do not really want to go into details here. One major difference is that we predict the convolutional weights from the head orientation and position of transmitter and receiver. So potentially, as the two of them move, there could be a different convolutional weight at every time step. This idea comes from signal processing, where you have a different convolution, a different filter for every position in space. So the filter itself in traditional processing is dependent on the position in time. So we model it in the same way here in the neural network, just have it much deeper and much more parameters. This network adjusts frequencies, does some small phase shifts, and corrects for everything that neural time warping couldn't yet correct for, particularly on the frequency side, obviously. I do not want to go into details for this, but I do want to talk about how to train this. Many works report that L2 loss on waveforms does not work well. The question is, why is this the case and what can we do against it? We provide some theoretical analysis of the problem of the waveform in L2 domain, particularly for spatialized audio. We have this lemma which is a bit hard to read, so let's go quickly through this step by step. It says there is a complex number y hat Let's draw this on the complex plane. Our y-hat is actually our binaural ground truth recording. Well, in frequency domain, so there would be multiple frequency bins. For simplicity, let's say there's just one frequency bin, so we have a single complex number representing our binaural recording here. And then the lemma says there is the circle around y-hat with distance epsilon and a second complex number y somewhere on the circle. Y is actually our predicted signal, again in frequency domain, and again just one complex number. We just think of one frequency bin. It easily generalizes to all of them. So we have y and we have y-hat, and the lemma now makes a statement about their relation. Actually, if you look at the L2 difference in frequency domain between y-hat and y, that is exactly the radius of the circle, epsilon. Parseval's theorem tells us frequency domain L2 loss is the same as time domain L2 loss. So you can think of epsilon, this radius, as the time domain L2 loss. And what we see now in the lemma is a statement about the expected amplitude and phase error. The amplitude error is the difference between the ground truth amplitude, the blue line, length of the blue line, and the predicted amplitude, length of the red line. And you can see that even for a fixed L2 loss in time domain, there are different amplitudes errors depending where on this circle our predicted point is. And the same holds for phase, right? The phase error is the difference in angles of these numbers. And again, if we move the red point around the circle, we have the same L2 value in time domain, but there are multiple possible phase angle errors that we can make. Now these integrals are a bit hard to visualize or like to parse, but we can plot them and then it's visualized and we can talk about them. Let's have a look at the expected amplitude error given the L2 loss first. Early in training, rectangle 1, if the L2 loss is still high, we can see that already the high energy components of the signal are pretty well optimized, have pretty low loss. And later, rectangle 2, it is even better, like all frequencies, all amplitudes among all energies are very well optimized. If we look at the same for phase though, we see early in training when the L2 time domain L2 loss is still high, rectangle number 1, phase is not optimized at all. And later in training, when the L2 loss is very low, phase is okay-ish for the high energy components, but still not well optimized for low energy components. So far the theoretical analysis. Can we validate this empirically? On the left, we trained our network just with the time domain L2 loss, and you see exactly what the theoretical analysis tells us, right? Amplitude is aggressively optimized initially in training, and phase is completely ignored, is not optimized at all. And even late in training, amplitude keeps improving, keeps being optimized, it's at a very good point already. Phase clearly lags behind. Our solution is to just add another term, a second term, an additive term that operates in frequency domain and penalizes the phase error. So essentially we say we have an additional term in the loss function that puts more emphasis on phase, and with this we see that both amplitude and phase are similarly optimized at a similar speed, and we obtain good values for both amplitude and phase, and not only for amplitude. Okay, let's compare this to some results that we obtain with a traditional signal processing baseline. It's the same example that you saw in the previous results, and you see again, transmitter monosignal white, binaural ground truth recordings blue. And here in orange, this is actually the signal that we predict with our system. And as a comparison, you can see that this is pretty accurate already in terms of L2, like how close it is to the waveform. And if I switch forth and back with the, here in red, DSP signal, you can really see that the deep learning, the end-to-end system achieves much better results. We also achieve much better results metrically. So if we look at the L2 loss in time domain, at the power spectral loss, phase loss, we outperform not only DSP, but also other deep learning-based approaches. And in a user study, our approach is also favorable in terms of cleanliness, spatialization, realism. So the key elements that we were using here, neural time warping, then this WaveNet style hypernetwork, and very important for accurate phase reconstruction, this altered L2 loss that we just discussed. You find many more experiments and much more analysis in the paper. I would also recommend to listen to the to the supplemental material that has a lot of examples where you can actually hear the effects on binauralization between DSP, between our system with L2 plus phase loss, with L2 only loss, and so on. Have a look at that, have a look at the paper, and thanks for your attention.